Hi! Today I want to talk about conjugate priors. In particular, I want to talk about the theory behind conjugate priors. Conjugate priors are a way of keeping our framework behind our prior selection. What I mean by that is, if we choose a prior, we want this posterior that we get to be in the same family as our prior. So what I mean is, if I have a family of distributions, this family is conjugate to my sampling distribution. If for any choice of x, our posterior is back in the same family. Let's first talk about what this means. I was talking about framework, about keeping the same framework. And what I mean by that is, maybe we have some framework for our prior. So maybe we think our prior, we don't know yet what exactly is the distribution, but we know it's a beta distribution. We model our beta distribution as our prior, and then we have some sampling distribution, and then our posterior is something completely different. And we already have this nice intuition about the beta distribution, and we completely fail to interpret the posterior, because now it's something completely different. Conjugate families are a way to make sure that no matter what happens, we are still, for example, in this family of beta distributions. And we can still use this nice intuition that we have. Let's see an example. Let's take the binomial distribution for some natural number n, and let's take as a family the beta distribution. So we have theta, and we have some parameters alpha and beta larger than 0. This is equal to 1 over the beta function times theta to the power of alpha minus 1, 1 minus theta to the power of beta minus 1. My claim is that this family here is a conjugate family with respect to this sampling distribution. How do we show this? We use Bayes' rule. Bayes' rule states that pi of theta given x is equal to the prior times the sampling distribution divided by this integral. But this integral, it's not a lot of fun to calculate. So I'm going to ignore it. Same for this constant and this constant right here. And I'm going to write this sign, which means proportionality. I can do this, I'll explain why shortly. So I'm just going to take the product of these two. So we have theta to the power of x times 1 minus theta to the power of n minus x times theta to the power of alpha minus 1 times 1 minus theta to the power of beta minus 1. And we can write this up as theta to the power of x plus alpha minus 1 and 1 minus theta to the power of beta plus n minus x minus 1. And my claim is that this implies that we have a beta distribution. This time with parameters x plus alpha and beta plus n minus x. I ignored all of the constants though. Why can I do that? Well, let's say we have a constant here, c. We know that this integral has to be equal to 1, because this is a density. But we can just then divide by c and see that this already gives us c, or 1 over c. 1 over c is equal to this integral. So we already know the constant. And given that we know what kind of distribution this is, we know that the constant has to be this beta function, this time in x plus alpha and beta plus n minus x. So we saved us a lot of work, and this is a very common trick. You see this trick pretty often in this video. So what do we have here? We have a beta distribution. We do this by choosing alpha and beta. And then we update by just adding x to alpha, adding 1 minus x to beta. And what you can already see is, if we have strong evidence, if x is very large, then the distribution should shift to one position. On the other hand, if n minus x is very large, it should shift to the other. I'm going to talk about these examples in a lot of detail in the next video about conjugate priors. Not necessarily the next video, but the next video about conjugate priors is going to talk a lot about the intuition and practical examples. It's going to have practical examples about how to apply this knowledge. But so far, this is only going to be a theoretical video about what you can theoretically do with conjugate priors, what the theory behind conjugate priors is. So to start with this, I'm going to have to talk about exponential families, in particular about natural exponential families. A distribution is a natural exponential family if it has the following form. We have some function h of x, where we just want that h is measurable and positive, or at least not negative, times the exponential function to the power of theta times x minus some function psi of theta. This function psi of theta, by the same argument as before, is already defined by the fact that this whole integral has to be equal to 1 if you integrate over the whole sample space. This integral has to be equal to e to the power of psi of theta. So you can solve this for psi of theta, so psi of theta is just the logarithm of this integral. Why are natural exponential families so important? They give us a very, very nice generalization of a lot of incredibly important distributions and much more that behave very, very nicely, that are very, very easy to deal with. And that way you can, if you have a theorem about the natural exponential family, you can prove a lot of things just in one swipe. And this is what we're going to do today. A couple of examples for the exponential family are actually what we just saw, the binomial. The normal, if mu or sigma squared are fixed. The exponential, of course, and many, many more. One thing I should note, these are technically exponential families, which have a slightly different shape. They don't have theta and x here, but they have some function of x here and some function of theta here. But you can just substitute theta for r of theta and x for t of x, and then you get this form. This can in some cases be pretty uncomfortable. We're going to see an example for this later. But first, let's prove a very nice theorem for conjugate families of exponential distributions. This theorem says we can immediately get a conjugate prior. So again, I have this function k of lambda and mu here. It's just going to be defined in such a way that this whole thing is 1 if you take the integral. There is one problem with this, but first I want to show that this is actually a conjugate family. We just do the exact same thing that we did a while ago. So this here I'm just going to call this pi of theta given lambda and mu. Lambda and mu are now again our hyperparameters. You notice that we have 2 hyperparameters, even though we have one parameter theta. That is very, very common. Usually our number increases by 1. So this here, it's again proportional to this here times this here, where I'm just going to ignore this. Also, I'm ignoring this. We can just solve it. So we have mu plus x here. And we have lambda plus 1 here. And this is proportional to pi of theta given mu plus x and lambda plus 1. So, looks like we're done. We're definitely not done though, because I've just defined this and I just said we choose k accordingly. That's not something that I'm allowed to do. Because yeah, sure, we can say k. I know what k is. K is just 1 over this integral. But how do we know that this integral exists? This is a very, very arbitrary function. For the beta distribution or something, it doesn't matter. We already know the beta distribution. We know that the normalization constant exists. Here, we just don't know. This could be very, very large. This could be infinity. And if this is infinity, we can't take it as a constant, so that's very bad. So we need some condition such that this is not infinity. For this, we need to talk about a very, very nice concept. It's going to be very, very nice, but it's gonna fall from the sky a bit. The good thing is that for this proof, we only need to do this once. And otherwise, for example, you could have asked yourself, okay, how did I come up with this beta distribution? And I didn't come up with it, I looked it up on Wikipedia, but that's beside the point. You don't want to ask yourself that for every single distribution that you see, because it's nice to have an intuition behind these things. And here you just have to think about how does he come up with this function. And okay, you can think very long about it and then come up with this. And thereby we get all of the other functions. So just wanted to mention how nice it is to have a general theory instead of having to prove this for every single distribution. Anyway, let's talk about convex hulls, because that is going to be important. A convex hull is what you get when you take all of the connection points. So the convex hull of a set is what you get when you take all of the connection points between the elements of A. And all A1 and A2. Looks abstract, it's really nice though. One example, I can just take, let's say I have this y and x axis, and I take 2 points, let's say 3. Then the convex hull is all of the paths that I can walk. So the path from here to here, here to here, and here to here. It's just triangle. And if I add another point, that's all of the paths to this point as well. Okay, why did I just define this concept? Because it turns out that this here is not infinity if mu divided by lambda is in the convex hull of the support of our sample space. So what do I mean by so h of x should be strictly larger than 0. Because, okay, you could ask what do you mean by support for the whole space, because we have different probability measures. I just mean that h of x is larger than 0. Because if you look at this definition, we have this function h of x. And actually, if we set theta equal to 0, we can immediately see that h of x is integrable. So instead of taking the integral, for example, from minus infinity to t, we can instead determine an antiderivative of h and take this integral. This is what's called the Riemann-Stieltjes integral. Not that important, but it's going to be a little bit important for the proof. And the proof of this is very nice, so I didn't want to skip on it. But the idea is just we have some positive point here for x. This integral is still going to be evaluated at x. Because the function here is strictly positive and h is also strictly positive on this. Okay, also we're going to demand that lambda is larger than 0. So let's prove this. So what I want to prove is this integral here. It's smaller than infinity. So let's take this integral. It seems quite hard to find the right way to solve this integral. But for the one-dimensional case, which is actually the case I'm looking at today, and for the almost all of the time, I'm going to look at the one-dimensional case because it's much easier to deal with, and usually the concepts that I want to show, they're the same concepts in the multidimensional space. It's much more difficult to deal with. In the one-dimensional case, we just have a line, right, for x. And we have 2 points. And mu divided by lambda is somewhere between these points. One thing I should have mentioned is that we don't just want them to be in the support, we want them to be in the interior. So we just don't want them to be on the edge. Because if mu divided by lambda is here, we have a small problem. Anyway, we have 2 points, and this is somewhere between these points. And in fact, the convex hull is just one line, because if we have some point here, we're just going to get the connection line here as well, and so on. How is this useful? I will show you how. Psi of theta? Psi of theta is the big problem here, because we don't know yet how to deal with psi of theta. Psi of theta is equal to this integral to the power of minus 1. This is to the power of minus 1. So if we restrict this space x, we're just going to make this interval smaller. But if this is to the power of minus 1, we have that this is smaller or equal to some restricted space, which I'm going to let be, which I'm going to define as an open interval from, let's say, I want to talk about some point x0, and I'm going to say what x0 is soon. Minus epsilon to plus epsilon. But then just by a standard integral inequality, we know that this is more equal than the length of this integral, which is 2 epsilon, times whatever the maximum of this function is in this integral. And why is this interesting? Well, we can talk about x0 being here or x0 being here, x1 being here. This whole thing only works if this here is actually positive, because it could be that this is negative. And then we wouldn't know what to do. So we have 1 over, sorry about that, we have 1 over 2 epsilon times this maximum. And we can make this interval arbitrarily small, so we get arbitrarily close to this point. We don't care about this constant, it's just a constant. x0 or x1. For x1 we're larger than this, and for x0, for x1 we're smaller than this, for x0 we're larger than this. So this here, we can divide this up, we can look at the intersection between theta and 0 to infinity. It's going to be very clear why we do this soon. Plus the whole integral of the intersection between minus infinity and 0. And we're going to, with this approximation, we're basically going to force this whole thing to be negative. So I'm going to take out lambda, then I have theta times mu divided by lambda minus, and now I want this, because we're on this positive space, I want this to be negative, so I'm just subtracting x0. And then I also have some constant here, but that's fine, we don't care about the constant. And here, same thing, I have some constants too, and I have this function, but now minus x1. And now I have some e function to the power of lambda times some coefficient which is negative. We know that this integral exists, at least on this domain. So we're done. Okay, one thing I should mention is that it's not exactly x1, but it's very, very close to x1. And this is not exactly x0, it's very, very close to x0, but it's enough that we're very, very close to these points. Also, one thing to note, when we update, we have the parameters mu plus x and lambda plus 1. And how do we know that we're still in the convex hull? Well, the convex hull here is just some interval. So this, if you just look in this, you know that this thing here itself is convex. And first of all, lambda, it's still larger than 0 because you just added 1. And if we take the ratio between these two, this is just equal to mu divided by lambda times lambda divided by lambda plus 1 plus x times 1 over lambda plus 1. This is just equal to a convex combination between 2 points. 2 points, one of which is just inside of the support of x, one of which is also in the convex hull. So the resulting point is still in the convex hull. So this is actually a closed group. I just wanted to show this because I've never seen a proof like this. If you use this technique, and we've actually shown that we have a closed family. There's one problem, which I'm going to illustrate by an example, because we need an example anyway. The example is going to be the exponential distribution. But I'm going to, and we've talked about this, I'm going to use a slightly different parameterization than what we usually see. I'm going to take this to be minus theta times e to the power of theta times x, but I'm going to let theta be smaller than 0. So usually we have a lambda here, which is larger than 0, but we have a minus lambda. Instead I just have minus theta, but then let theta be smaller than 0. Because then we have the exact form of the exponential family. We can just let this be equal to e to the power of theta x minus the logarithm of minus theta. Or I'd write it in this form, because this here is then going to be our psi of theta. Now we want to apply the theorem. We have a conjugate family given by e to the power of mu times theta minus lambda psi of theta, where we want lambda to be larger than 0, and we want mu divided by lambda to be in the interior of the convex hull of x. X in this case is just 0 to infinity, because this support doesn't change. It's always 0 to infinity. And the convex hull of this line is just the line itself, because every convex combination is in this line. So we want this here to be to be larger than 0, which is equivalent to mu being larger than 0. So this is equal to e to the power of mu theta times, now I'm going to plug this in, this is minus the ln of something, we have a minus here, they cancel, so we have minus theta to the power of lambda, and then if we substitute z to, again, this is still proportionality arguments, I'm still not talking about the constant because the constant doesn't matter. This is proportional to, when we set z equal to minus theta, e to the power minus mu z times z to the power of lambda, and you know that this here is a gamma distribution. Also, if you look the gamma distribution up, actually this parameter can also be smaller than 0. It has to be larger than minus 1, but it could be smaller than 0. And in this case, the theorem, it demands lambda to be larger than 0. So lambda is unnecessarily limited, one could say, but lambda being smaller than 0 is often a case which we're not too happy about. This is mentioned in the paper from which I got this result from. This is not a result from the textbook. The textbook has a similar result, but I wasn't too sure about it. I'm going to link the paper in the description. It's a very, very nice paper. It also has a converse direction for this theorem, for when the converse holds that there's no bigger family. But for this case, it could be smaller, but just as the theorem in the paper says, or just as the authors of the paper say, it can be unfavorable, for example, when the base risk is not going to be defined. So you can't actually define Bayes estimators for lambda being smaller than 0. Anyway, so we finished with this proof, and we have one example, which is very nice. I just want to finish with one other theorem. And the way I'm going to motivate it is that, for example, if we have a normal distribution, which is also a prior distribution, a conjugate prior distribution to something else, some other very common situation, normal distribution is very centered around this mean. So this can be very fitting. For example, if we're pretty sure that our value, it's around 3, you're pretty sure it's around 3. But sometimes you're not sure. Sometimes you think, okay, it could be 3, but it could also be 4. Problem is 4 is pretty far away. How do you model this with a normal distribution? By staying within your framework. Conjugate distributions of the exponential family can be quite restrictive. You should be able to model the situation, but you can't. But there's an easy solution, at least for this problem. You just take another normal distribution and you scale both of these. You add them and you scale them down. So you divide by some constant. And depending on how hard you weight this one, you can divide this one by a larger constant and this one by a smaller constant. And then you get a new distribution. So you get a convex combination of distributions. And this is still in our framework. We can expand our framework a little bit. This is going to be the statement of the theorem. So if we have pi of theta given lambda I and mu I, our convex combination, so the sum of this times omega I, where we define the sum of omega I to be equal to 1. This whole thing here is a natural, not a natural, but it's a conjugate family. We're going to show this. How are we going to show this? Well, we're going to use a really nice trick. Let's say we have a random variable. I'm going to call this omega, although I know some of you might heard this notation. We're going to define omega by the probability of omega being equal to I to be equal to omega I. Because then we can define a new parameter theta to be equal to omega times theta I. How am I going to define theta I? I'm just going to say theta I is distributed according to pi of theta given lambda I and mu I. One thing I should note, it's not omega, it's the indicator function of omega being equal to I. So depending on what value omega takes, we get this prior distribution. Because then, this is actually the interpretation of convex combinations. The distribution of theta is exactly this. Because it's the sum of theta given that omega is equal to I times the probability of omega being equal to I. And we know this, just the way we defined it. Now we can just think about what is the probability, what is the distribution of theta given x. We can just sum over all values of omega. I should say I is just some number between 1 and n. N is just some large number. We can take as many convex combinations as we want. So this here, pi of theta, by taking all cases into account, this is theta given x omega equal to I times the probability of omega being equal to I, but this time given x. And we don't know what this is, but we do know what this is. This is equal to this. Now omega being equal to I just tells us what theta is. It's theta I, and that's the only thing that it tells us. So we have the posterior distribution given theta I, and we already know this because we've shown this from the last theorem. It's pi of theta given lambda I plus 1. and mu I plus x. And we still have this distribution, which is more difficult to calculate. Actually, we're already done, but maybe we just want to know what this is. We can just use Bayes' rule again. So this is proportional to the distribution of x given omega times probability of omega being equal to I. We know this. We don't know this yet, but we can again integrate now over all values of theta. So we don't know this value, but we can just integrate over all values of theta to get this value. Now we have to multiply with the probability or with the distribution of theta given. But this here, this is just a sampling distribution. So we have h of x e to the power of theta x minus psi of theta. This here, this is the distribution of theta, the prior distribution of theta, given lambda I and mu I, and because we know that omega is equal to I. So this is going to be equal to, first of all, our constant k of mu I and lambda I, and then e to the power of mu theta minus psi of theta times lambda, here again with the I index. This constant we can plug out. This constant we don't care about, but these here, oh sorry, this constant is going to stay, sorry. If we take this whole integral, we already know what this is going to be, because this has the exact form as in the last theorem. This whole integral is going to be equal to 1 over, so again from the last theorem, or by the same calculation, this is 1 over k of mu I plus x lambda I plus 1, and here k of mu I, k of lambda I. So this constant survives, but the rest, if we integrate with respect to theta, we get very, very similar to the calculations that we did for the last theorem. We just get that this has to be a normalization constant. So we get the ratio of these two times omega I. This is our constant here. So this is equal to this divided by the sum over this. So if we want to know what this is, this here it's equal to one component divided by the sum over all components. Yeah, because the values have to normalize to 1. So we actually not only have the fact that this is a conjugate family, but we have a nice formula. We know that it's a convex combination of the posterior distributions from last theorem, and we know that the factor is the prior weight, omega I. So this factor here, this is the prior weight, omega I, times the ratio of the normalization constant. And you could think about this as like the ratio of, okay, how much weight did I put into this now that I've updated my information. My prior normalization constant used to be k of mu I and lambda I. Now I have a new normalization constant, so I have to update my weights as well. This is also very common for many algorithms. For example, the expectation maximization algorithm for mixtures of normal distribution has the exact same thing with updating the weights. Anyway, I hope I have given you a bit of a theoretical oversight over the conjugate distributions and the theory behind them. I'm going to provide material for further learning, and I'm going to try to make nicer drawings for next time, because I can see that this was a bit hard to read maybe. One last note, which I've already said before, but maybe I cut it out, is that conjugate families let us keep our framework. That's why they're important. And I'm going to talk about this in detail in the next video about conjugate priors. See you.